Okay, does everybody have a computer today?
My brain is a computer.
Good. It's a more powerful computer than any Windows machine, that's for sure.
Hot like that. Sorry.
It makes me question what system he likes.
What system does your brain use?
Over here now.
Oh, you did? You got one of those? I'm sorry, there was a lot happening. I was like looking at the several things happening, and I was going to go break my finger and this and everything, but anyways,
Okay, today we're going to continue the Hardy Cross method. Now, what we're doing with Hardy Cross method is we're trying to, how do I make that real small? All right. What we're trying to do with the Hardy Cross method is identify what is the flow rate through every pipe in the network, and also sometimes we'll calculate the pressure at junctions. But solving the flow rate through the pipe is kind of the goal. And what you'll remember from our previous example is we were starting with fixed R values. So here was our previous example where R was just some collection of resistance factors. It took into account the pipe friction, the length, the diameter, all of the factors that are going to result in resistance that goes into the Darcy-Weisbach equation. And we started with some guess of the flow rates, and we know the flow rate going in, the flow rates coming out, and so as long as at each of the junctions continuity is honored, meaning that flow in and flow out are equal, then eventually this method will balance everything out. It will find the equilibrium flow rate through each pipe. So we're going to take a little bit more sophisticated approach in today's example. This example, we weren't really updating F values to account for the changing flow rates. This time we will. And so what I'd like you to do is turn the paper to the second page, the one that says Example 2, Hardy Cross Method with Microsoft Excel. So what you'll have to do, first of all, is split the flow that is coming in and going out. You're going to make your own assumption of what the flow amount and flow directions are. So write that on the paper and do it in pencil in case you need to make a change to your assumption. And then we're going to use the student start file that's available on Blackboard. It's just already added all of these column headings for you. With that student start file, then you'll be able to begin inputting the initial guess flow rate, and then we'll kind of go through the process together, starting with the fully turbulent flow assumption for calculating our initial F, but then we'll have updated F values from there. So the first thing to do is, in this printout, draw, for example, the 1 cubic meter per second that comes in at A. What is the flow direction and the flow amount through the pipe AB and the pipe AF? So you can assume anything you like. You can have it split 50-50, you can do 40-60, you could have all of the flow go through one pipe and 0 through the other. But what you have to make sure is that in every junction in your network, that flow in and flow out are equal. Now some of you, all right, so here is our initial flow rates and the initial guesses that I came up with that I'm going to be putting into my spreadsheet, but you use your own flow rates. It will work out. Is, okay, the flow is split half and half, and then here, this 1.2 I sent 0.6 and 0.6, and then if we have 0.6 and 0.5, that means it's 1.1, which means half a cubic meter per second must be coming through here, which means there's 0.1 left over, and now in equals out at each of the junctions. Our control point is junction A. That's where the pressure is known. And at the end of this process, we're going to calculate the pressure at each junction, and we're going to be starting with this known pressure at location A. So before we go any further, are there any questions related to just flow balance in general, or your specific flow balance numbers, or the guesses that I came up with? Any questions at all?
So it seems, forgive me if you've already discussed this, that even if you have zero flow, you can still have an R value and...
That's right.
Okay.
Yep, the R value is independent of the flow rate.
Okay.
Yeah, we'll calculate the R values in the spreadsheet to reiterate how we do that. Now remember, the whole reason we're doing this is the guts behind the computational mechanism that's in water gems. And so we need to be able to do it manually to understand how it's solving. You don't want to use a tool without understanding the tool, and so this is us understanding the tool and learning it. So if you have that template file that I provided, I think the starting point should look like this. All right. And if you don't have your computer today, that's fine. You can just watch. And of course, remember that this video is being recorded so that you can go through it click by click later on. All right, so in our first iteration, I'm calling this upper loop, loop 1, and the lower loop is loop 2. Does anybody remember what's our convention for knowing whether a flow is positive or negative? Like, for instance, in our initial setup, I said that this is 0.5 cubic meters per second. Is that positive 0.5 or negative 0.5?
Positive.
Positive. That's right. And how do we know that this is a positive 0.5?
It's clockwise.
Because it's clockwise, right? So we say in this loop, clockwise is positive, and so for instance, this flow, when we're typing in the flow rates, that flow will be negative because it's against the clockwise direction. Now what about these pipes that are in both loops? So the 1.1, for instance. Do I call that a positive flow rate or a negative flow rate? Well, from the perspective of loop 1, this top loop, it would be a negative flow rate because it's going against the clockwise direction. But if I'm in the perspective of loop 2, which is the lower loop, it's in the same direction as clockwise. So then that would be a positive flow. So one of the tricks that we emphasized during the example on Friday is that when we set this method up, we need to change the sign of the pipes that are in both loops. So we'll pay special attention to that. All right, so iteration 1, loop 1, we're going to have pipe AB, pipe BC, CE, EF, and AF. So this is a relatively complicated pipe network. We've got 5 pipes that are in loop 1. The K sub S, the equivalent sand roughness, is going to be the same for all of them. I think that the handout says that in this example it's an epsilon of 0.3 millimeters. And so we can say equals 0.3 divided by 1,000. 0.3. All right, so that's our K sub S value. And then just enter in some of the data here on these pipes. For instance, the diameter of pipe AB is 0.5. BC, the diameter is 0.65. CE is 0.6. EF is 0.7. And AF is 0.4. All right. Calculate the cross-sectional area. So pi times the diameter squared divided by 4. And we can double click and it'll apply that same formula down through all of them. And we'll put in the applicable pipe lengths. So the pipe length is 220 meters for AB, is 100 meters for BC, 150 meters for CE, 80 meters for EF, and 180 meters for AF. Okay. So we haven't really done much calculation yet, just calculating the areas. But here in the F, we're going to estimate the F value assuming, at first, fully turbulent flow. It's better than just a random guess for F value. Remember, the fully turbulent flow assumption is if Reynolds number is really big, then the Jane equation just simplifies to 1.325 divided by the logarithm of K sub S divided by 3.7D, and then all of that squared. So that's what I'm going to do here for the fully turbulent flow assumption. I'll do 1.325 divided by the logarithm of K sub S divided by 3.7 divided by D, close that, and then square the logarithm. So this is what the F value would be if the flow rates are really high through that pipe. So that's not going to be the F value we use in the next iteration. We'll use the full Jane equation in the next iteration, but for now it's a fine estimate for iteration 1. There's going to be a lot of changes between iteration 1 and iteration 2. Any questions so far?
Why are you allowed to assume that?
I'm allowed to because I'm going to check it later.
Oh, okay.
That's what allows me, like what gives you permission to make that assumption is that you'll improve on it at a later date. I won't make that same assumption in iteration 2 though.
Okay.
All right, so R is, the formula for R is here. Okay, so it is equal to F times L divided by 2 times G, 9.81, times the area squared times the diameter. So our R value for that first pipe should be 10.1. And like what is R? Well, R is the coefficient that goes in front of this expression, and it's the Darcy-Weisbach equation. So it would tell you if you put the flow rate in cubic meters per second and square the flow rate and then multiply it by R, it would tell you the head loss in meters. So it's not totally meaningless. It's something that goes into a pretty important equation. It's just the aggregation and simplification of part of the Darcy-Weisbach equation. All right, so we can drag that down through all of the pipes. And then N is 2 because we're using Darcy-Weisbach equation. It would be 1.85 if we were using Hayes and Williams. And now we have to start putting in our guess flow rates. All right, so the guess flow rates that I had may be slightly different from yours. Let me just paste this again so that I can see them as I work. You can put in your flow rates, and I'll put in mine, and hopefully by the end, if we've both entered all the equations correctly, we'll get convergence to the same amount, even though we had different guesses to begin. All right, so clockwise positive, I'm working in loop 1, so that means that this 0.5 is positive 0.5. Then pipe BC, Okay, so I said the arrow is going up, which is against clockwise, and so that makes it negative 0.1. CE 0.5. EF, that's opposite clockwise direction, so that's negative 1.1. And then also anti-clockwise for pipe AF, so negative 0.5. Now, you'll note that all I'm doing so far is loop 1. I'm not going to start filling in the data yet for loop 2 because for any of these common pipes, I wouldn't want to start with my initial guess. I'd want to start with the best updated value. So that's why I wait until doing all of loop 1 before I put in the data for loop 2. Okay, so let's do R times Q times the absolute value of Q, so ABS of Q, and do it for each of the pipes. And then likewise we're going to do N times R times the absolute value of Q and drag that one down. All right, and then at the bottom of each we need to add up because the equation that we're going to be applying, this correction equation, this one, it requires you to have the sum. Okay, so we are going to, here's that equation. So we want the sum of these things above it and the sum here. I put that in italics just to kind of make it clear that that's like a combination. Let me pause for a moment and see if... Okay, so the formula that we're going to apply, this correction formula, we have to have the negative of this one divided by that one, and because we want it to remain as a relative reference, we're going to repeat that calculation rather than anchoring and dragging it down. So equals minus that divided by this equals minus this divided by that, and so on and so forth. So then the corrected Q is our original guess plus the delta Q. And then the velocity, it says here the absolute velocity, so let's do absolute Q divided by the area, and that tells us the velocity through the pipe, which is going to be useful the next time we calculate the F value, because you can see in the cell next to it we're going to calculate the Reynolds numbers, and so that'll allow our next guess of the F value to be more accurate than our first guess was.
What was the corrected Q?
The corrected Q is the original guess plus the delta Q. So Q plus delta Q. Are there other questions? Okay, Reynolds number is V times D divided by the kinematic viscosity of water, 1 times 10 to the minus 6th. So you can just type in 1e minus 6 and enter. All right, so we've got Reynolds numbers. And then here in percent change, what I'm looking at is how much did our flow rate change in this iteration. And this is going to be an indicator of whether our solution has converged. What we want is for the corrected Q and the initial Q to be within 1% of each other. And so let's see if that's true. The initial minus the corrected divided by the corrected times 100. And we're not even close yet. Our initial guess was 17% too small. And you can see there was a huge change in the flow rate for pipe BC. All right, so we're not yet converged. All right, now let's go to still iteration 1, but loop 2. Okay, so now in loop 2, we have pipe CD.
I think you're one over.
Thank you. Okay, there's CD, CE, EF, and DF. Now, let's bold the pipes that are common to help us remember about that flipping the direction and adding the negative sign. So CE is a common one. So I'm going to highlight both of those and add bold formatting. And then the EF is also a common pipe. So EF is in both loops, and so I've just bolded it there as a reminder to myself. Okay, so they all have the same K sub S value. So I'll just put in 0.0003 and drag that down through. The diameters for each of the pipes are given in the figure. Okay, so CD is 0.85, 0.6 for CE, EF is 0.7, and then DF is 0.5. We don't have to type the formulas in again. If we just highlight these four and then Control C and Control V, what we paste is the equation, not the amount. And so by pasting the equation, it looks to the left and calculates the area based on the diameter in that row. So you could type it over from scratch, or you could just paste the equations. All right, now the lengths. Pipe CD is 80 meters long. Pipe CE is 150. Pipe EF is 80 meters. And pipe DF is 200 meters. All right, now we'll use the Jane equation for this first round of F values. So I can do the same thing as I did before. I just want to copy 4 formulas and paste 4 formulas. And now the R values, I can do the same thing. I can highlight 4 of them and paste 4 of them, and it's going to calculate the R values just based on all of the numbers that's to the left. And so if I click on one of those, you can see it's doing the formula based on the data still in that row. Okay, the N value is 2 for all these pipes because we're going to continue to use Darcy-Weisbach equation for our energy loss. All right, now with the Q, this is where we need to be kind of careful. We will have the initial guess for pipe CD, and my initial guess for CD was 0.6, and so I'm going to put in negative 0.6 because it's against clockwise since that arrow is going up. So negative 0.6, and you put in your flow rate there. Now CE, I don't want to put in my guess flow rate because I can do better than that. I now have an updated flow rate. Over here in the previous loop, it was saying this corrected flow rate for CE. So I'm going to say equals negative of that. And the negative because now I'm in the perspective of loop 2. So the directions are different whenever you're in the other loop. And then the same thing for EF equals the negative of this corrected flow rate. And then DF, I don't have anything other than my initial guess flow rate of 0.6. And that was in the same direction as clockwise, and so it's positive. So 0.6. Okay, now I need to do R times Q times absolute value of Q and sum it up at the bottom. So I'm going to highlight these four. I'll have to change the sum function though. So let me just highlight those four and paste. Highlight these four and paste. I'm pasting the equation. And then I'll sum and italicize just as a reminder that that's the sum. Scroll sideways, I'll apply that same sum formula to the cells that are above it. And I have to manually type in this equation, equals negative this divided by that, 4 times. Okay, then the corrected Q is your original flow rate in that row plus the delta Q. And then I can highlight the absolute value of the velocity and paste the formulas. And do the same thing with the Reynolds number and the percent change. Okay. Let me pause for a moment and see if anybody needs any help. Okay, so let's finalize this by getting the iterations done. So now we're going to do iteration 2, and we can copy all of this same data about the pipe network. So Control C, Control V to paste it. But we're going to use the full Jane equation for the F values this time. Okay, so it is equals 1.325 divided by ln of K sub S divided by 3.7 divided by D. And now we are going to do the right side of the equation, so plus 5.74 divided by the Reynolds number. The Reynolds number I'm going to use is this Reynolds number from the previous iteration. So that Reynolds number to the power of 0.9. And then all of that squared. So we're assuming that the Reynolds number is in the ballpark of what we had in the previous iteration, and each time we repeat this process there's going to be less and less change, so it'll eventually converge on the correct Reynolds number. This is the Reynolds number based on a guess, but eventually it will become the actual Reynolds number. Alright, so you see our initial fully turbulent flow assumption wasn't so bad. You know, just guessing with fully turbulent flow, we said 0.0174. 0.0178 is our updated adjusted flow rate, F value. So we can drag that down all the way and calculate all of the F values. Alright, R values, highlight all of this. And I guess might as well do the ends too. So Control C, Control V. So now what it's doing is it's calculating updated R values based on this new F that we've got. Okay, for Q, let's not just repeat these initial guesses, but we'll use the most recent guess of F that we have. And so for AB, it's the reference up to here, the corrected flow rate. Okay, BC, here's our best BC flow rate. Our best CE flow rate equals minus of that one. This is the most recent CE flow rate that we have, but it's in the perspective of loop 2, so we need the negative sign. Same thing with EF, equals negative of that flow rate. The negative sign because anytime you make a reference to the other loop, you have to change the flow direction. AF. All right, and then we can copy and paste all of this. Control C, Control V, and it works out beautifully. We're getting better. This is getting closer. If you look at the percent change, it was 17% change, now 3% change, 3,000% change versus 120. We're getting closer. We're not quite there yet. Flow rates for here. All right, so our best CD flow rate guess is this one. Our best CE is we just calculated it. So equals negative of this flow rate. Same thing for EF, equals negative of that flow rate. And then our best DF comes from the previous iteration. Okay, so we've got the flow rates that we want. And now let's copy all of this. So this is all the calculations associated with loop 2. So Control C, and then paste it into place. And it does the sum of all the corrections. It finds the delta Q, the corrected Q. And so you can see that we're not converged yet, but the difference is much smaller. And that gives us an idea that things are headed in the right direction. Now from here, we can do subsequent iterations really easily. We just highlight everything, Control C, Control V, and all we have to change is the iteration number. That's the third iteration. You notice that this pipe BC is still kind of stabilizing. Everything else is down to 1%, but pipe BC isn't quite there yet, simply because the flow rate is so small. So if we go into a fourth iteration, Control C, Control V, then here in the fourth iteration we see that we're about 1%, even for that pipe BC that was being problematic before. So now these are the corrected flow rates. These are the actual flow rates through the network. You'll notice that pipe CE is the same flow rate, just a different direction based on the perspective of which one is clockwise. Same flow rate for EF in both of them. Now, for those of you who started with different numbers, do you end up with the same flow rate answers in the end? I see one nodding head. Nobody else got to these same flow rates? All right, so what that means, if it doesn't converge to the same flow rate, it means there's a mistake somewhere in your spreadsheet. And I'm happy to help you find that mistake. I'd suggest that you stop by during my office hours or just anytime I'm in the office. And it's good to have a working example of this method available so that you can use that same working example on the homework assignment. So we're out of time for today. So save this And just briefly on Wednesday, what we're going to do is we're going to address the question of what's the pressure at each junction. So we have the flow rate through each pipe. It'll take another 2 or 3 minutes on Wednesday for me to show you the pressure at each junction. But if you don't have these flow rates yet, you need to fix it so that you have them. So either you work on it or let's work on it together, but by Wednesday you should have the functioning operational spreadsheet with the correct flow rates. All right, so I'll see you then.